Well, welcome everybody. So today we're going to be talking about climate change basics and impacts to agriculture in Nebraska. And so these are the four main points that I'll be talking about. Climatology, what is climatology and the difference between weather and climate. Look at some historical climate trends, how have things changed in Nebraska since we've began record keeping, and then compare that to projected climate change. What do we expect in the future? And then look at some of the primary impacts as related to agriculture. So I usually start out weather and climate presentations with this slide, and that is that weather and climate, some people use the term interchangeably, and they're related, but they're not the same term. And so I say they're cousins, but they're not the same person. So weather represents what I'm wearing today, whereas climate is the whole spectrum of clothes that I have in my closet. So today it's November 15th. In my office, it's a sunny day. It's relatively warm. It's not windy. Those are kind of the weather conditions, the day-to-day, whereas climate is the long-term, and it's the whole spectrum of weather observations that you can expect. But if you're into baseball, you can say that weather is your at-bat and climate is your batting average. So that's a little bit of the difference between weather and climate. And if you are a visual person, we can look at this graphically. And essentially what this is showing you is weather that is in the blue here. That's your day-to-day variation. This is starting in January 1 and going through the end of December. So it's showing you the weather throughout the year, and the brown line here is your average. So that's your average high, average low, and then your record high and record low temperature. So again, the blue is your weather, and the other colors here represent the climate conditions, the averages and the extremes. So weather, and in the brown would be your climate. One of the things that's really important to understand when we're talking about climate is that climate is composed of a system, and that includes the atmosphere, the land, the ocean, and the ice and snow. So the global climate system, it's made up of these components. Another big component of the climate system is people, and we don't necessarily think perhaps about people as a part of the Earth climate system, but it's a very important part, and we change the landscape, we irrigate agriculture, we build cities, there's lots of things we do that changes our landscape and our environment that does ultimately influence our climate. Another thing that I like to mention to people when I talk about climate is the various spatial scales of climate, which might not be something that you think about very often, but global climate, it's climate of the Earth, and that's the things that control the climate of the Earth is variation in the solar output, solar variability and sunspot cycles. There's volcanic activity, like Mount Pinatubo that erupted in the 1990s, and that influenced our global climate conditions for a short period of time. Another thing that's really important, becoming much more important, is greenhouse gas levels. That's a way in which we influence our global climate. There is kind of the macro scale, thinking about climate of the Midwestern U.S. We have a very continental climate, we have warm summers and cold winters, it can be windy here. So things like the latitude that we are on Earth, how close we are or not to a body of water, what the topography is, what the prevailing wind directions are, that controls the climate at kind of this macro scale. Then we have mesoscale, so localizing it to the climate of Nebraska, the fact that we're at the mid-latitude, the fact that we're not close to a body of water, the elevation differences, say eastern Nebraska versus the sandhills versus western Nebraska, that influences the climate, as well as the local topography. So those are some again, factors that influence climate at the local scale. And then we can think of the very micro scale, looking at climate on the scale of a farm or within a city, in terms of, do you have trees or not? Are you shaded? Is there evaporation? Is it Is it a paved area or is it a natural landscape? What is the slope direction? If you know, on your farm, you can think of your fields and the top of the hill versus a slope versus the bottom of the hill. Those are going to have different drainage patterns. They're going to have different soil moisture because of how the water flows, or ground surface type, whether it's grass cover or cropping systems or so forth. So all of that has to deal with climate of the local area. So all of these factors, when we kind of combine them, this is how we get our precipitation climatology for the U.S. So in the color scale here, it's wetter in the southeastern U.S., and then it gets drier here in the west. But we do have some high precipitation here on the west coast. We have prevailing winds that come from the west in general in this part of the country, and you can see the very strong precipitation gradient in Nebraska, where it decreases by 50% when you go from east to west. And most of us are probably aware of that fact, but it's a function of prevailing winds, whereas moisture is brought up from the south, from the Gulf of Mexico, so that you get high moisture here, and you have higher elevation. A lot of the precipitation occurs in the high mountains, and so it's drier that comes off the Rockies. And so western Nebraska is quite dry. So this very strong precipitation gradient is a significant part of our climate here in Nebraska in the central U.S. So drier from the west and moist air from the south. Something like a latitude where we are kind of on the globe, that significantly is a factor in the temperature climatology. So these are annual average temperatures, and clearly what you'll see is it's warmer in the south and it's colder in the north. And Nebraska, again, kind of lies in this somewhat transition zone here in the middle latitudes. So our temperature is largely a function of where we sit on the globe. So I've talked about spatial scales of climate. We can also think about temporal scales of climate. So if we look at Nebraska's annual average temperature, we'll notice that there's a lot of variability from year to year. Some years are warm, some years are cold. We can put a trend line through it, and this gets at kind of the climate change. What is the trend? What is the signal in temperatures for Nebraska? And you can see we've warmed about a little more than a degree, about 1.5 degrees overall for the state of Nebraska. But there's also this variability that's taking place. And so we've got this overall warming trend and then the variability about the trend. So we're looking at two different factors here, the climate variability and the climate change signal. And the variability is probably what we sense most from season to season and year to year. And a lot of that, part of that has to do with kind of these teleconnections, these large-scale patterns in the Earth climate system. El Nino is one of them. And so here's a picture kind of the global ocean surface temperatures. It's a departure from average. And what happens kind of in the equatorial Pacific, kind of around the equator in the Pacific, this big basin of water in the Pacific Ocean, that has a lot to do with global climate patterns and getting at that variability, kind of those purple lines there. That's driven in large part by what's going on in the Pacific Ocean. We can look at teleconnection patterns in the Arctic Ocean, in the Atlantic. There's all these different kind of patterns or modes of variability that impact our climate kind of from year to year. So El Nino is a good example of one of those. And typically at the outlook for the upcoming winter, actually it's calling for chances for a warmer than normal winter. And that's largely driven by the fact that we're going into an El Nino pattern, and that's expected to last throughout the course of the winter. So warmer than normal is what the prediction is for this winter. One thing that's really indicative of our climate, which you probably are all very well aware of, is again how this variability plays out, and the fact that we can go from years like 2011, where we had a really significant flood, particularly in eastern Nebraska. That was a function of both local heavy rainfall as well as high snowpack conditions, and a wet winter and spring in the upper Missouri Basin, and that has impacts when the water goes downstream through Nebraska. And that flipped in 2012, where we had a very warm and a very dry year, one of the warmest and driest years on record in Nebraska. So this back-to-back variability is something that we deal with historically. So now I'm going to get into kind of talking a little bit about climate change because of what we're doing and because of human behavior and the fact that we're emitting these greenhouse gases into the atmosphere. And I mentioned that people were a part of this global Earth climate system. And so we're going to go back to kind of physics class and take a look at the climate system at a very basic level so you can understand the greenhouse effect, because it's a really important part of the Earth climate system, and it's something that people misrepresent and misunderstand. So we're going to talk about the greenhouse effect. So the sun emits shortwave radiation. The Earth emits long-wave radiation, and that's solely due to a function of their temperature. The sun is obviously much, much warmer than the Earth is, but they both emit energy. Any object that has a temperature emits energy. So the sun is shortwave, that's the sunlight that we see, and the Earth emits long-wave or thermal radiation. Okay. So I'm going to step through this little schematic that talks about the greenhouse effect. So the sun is emitting solar radiation or shortwave. The Earth has a certain temperature and it's emitting long-wave radiation. So in this schematic here, this in white and blue is the atmosphere. And the atmosphere is composed of gases, and we emit what are called greenhouse gases. That could be carbon dioxide, methane, nitrous oxide, water vapor. All of these different gases are what composes the atmosphere. So when solar radiation comes down, it goes through the atmosphere. It could be reflected by clouds. When it hits the Earth, could be reflected. If there's snow cover, it could be reflected by the Earth. It could be a large part of what hits the Earth is absorbed by the Earth. So the Earth takes this shortwave solar radiation, absorbs it, and then emits it as long-wave radiation. That's what you see here, this radiated heat. This radiated heat, it can be absorbed by clouds and re-emitted back to Earth, or it can go through clouds. And what is illustrated here is what we call the greenhouse effect. And we actually need the greenhouse effect to sustain life on Earth. If we didn't have it, then we would be about 60 degrees colder than what we are now. So it's really important to have that we have the greenhouse effect. But what we don't want is an enhancement of the greenhouse effect. And that's what's been taking place over recent history. So this long-wave radiation, again, that's emitted from the sun. The Earth absorbs solar radiation and it emits it as long wave. Well, the greenhouse gas is in the atmosphere. It absorbs that long wave radiation and it re-emits it back to Earth. Absorption and re-emission of long wave radiation. So it's this piece here that's adding to and increasing our global average temperatures. This is just a simple physical representation of what's going on, kind of the physics of the atmosphere. So it all has to do with incoming radiation, outgoing radiation, absorption, and then re-emission in the long wave. This is what is causing our temperatures to rise. Okay. The reason that we know that we're a big factor in this is that we've observed CO2 in recent history. CO2 is a very well mixed gas, and it lasts on the order of a century. So CO2 that was emitted through us or through natural reasons that was emitted 100 years ago is just now phasing out of the atmosphere. So it lasts a long time, and it's a very well mixed gas in the atmosphere. And what we've done for several decades is measure CO2 in the atmosphere. So we know that it's been increasing. This happens to be a picture of the observation network in Hawaii. And there are other places on Earth that measure CO2. And we can go back in time and look at what's called paleoclimate records. We can look at ice cores and look at the bubbles in the ice core and see how much CO2 was in the atmosphere at that time. So we have observations of CO2 and other greenhouse gases. We can also look at climate models, and so what this graphic is showing you is global average temperatures, and it's also breaking it up by land temperatures, and only land and only ocean. Ocean covers about 70% of the Earth's surface. So this graphic goes from 1900 to about the year 2000. So over 100 years, we can look at climate models that only use natural forcing, so volcanic eruptions, solar variability, things that naturally happen in the atmosphere that impact our climate. We can run a climate model and see how well it compares to actual observations, which is in the black line here. Then we can run the climate model using both natural and human-caused forces, and that's what's seen in pink here. And that much better recreates what has happened when we use both naturally occurring variability in forces as well as what humans have done. So it's a very good indication that the way we're changing our landscape and what we're doing has an influence on global climate. So the graphic I showed earlier from Hawaii measuring CO2, that covers kind of this time period right here. And in this graphic, we're going backward in time, about 400,000 years. And this is from ice core records taken from Greenland and Antarctica. And we see the variability over time. This is only in carbon dioxide levels. This is in terms of parts per million. In 1950, we were over 300 parts per million, and currently we're at over 400 parts per million. And we stay over 400 parts per million year round. But historically, if we look back in the hundreds of thousands of years time frame, we never really went above 300 parts per million until the Industrial Revolution, and lots of changes to our landscape and what we're doing to the environment really caused this recent spike. So it's here that our concern is. So just a little bit about climate models and how they work, and we could really spend a whole course on this. But here's my kind of middle school level schematic of how do these climate models work. And essentially they represent the ocean, they represent the landscape and the atmosphere, and they also represent interactions between the ocean and the atmosphere, the landscape and the atmosphere, clouds, ice that covers the ocean, land type, landforms, the Rocky Mountains. All of these are represented in mathematical ways in climate models, and that's how we represent our Earth. And essentially that forms the basis of our understanding of our environment and how we can make these predictions. Okay, so just a couple more slides here before I get into kind of the historical change and future projections. So climate models use what are called emissions scenarios. And these terms here, these are called representative concentration pathways. And there's 4 different emission scenarios that are used globally. So I mentioned that we're at about 400 parts per million CO2 currently. This is the high emission scenario, and it goes to 1370 parts per million CO2 concentrations. There's a 6.0, and these are different variations. All we're doing is increasing CO2 to a different level than what we are now. So this 6.0 goes to 850 parts per million. And there's two others. There's what's called 4.5 and then 2.6. And this is kind of the 8.5 is termed as the business as usual approach. So that assumes that we don't necessarily change what we are doing on the landscape. Whereas this assumes that we're going to change our behavior and reduce CO2 emissions, or keep it at a stable level compared to what it is now. And this little graphic in the middle here, it's basically going from present day out through the next 100 years. And this is CO2 concentration, so you can see the different levels of CO2 concentration from a kind of stabilizing compared to what we are now, as opposed to continued increases of CO2. Is that curve going to continue to go up, or is it going to level off? Okay, so I'll get into talking about what has happened in the past. And what I'm showing here is kind of Nebraska as it relates to the U.S. as a whole. So this is a look at annual average temperatures, and for much of the U.S. and for much of the globe, we have warmed. And the rate here, so in Nebraska, you see the different divisions, what are called climate divisions in Nebraska. So about a degree and a half, roughly, amount of warming over the last 100 years. This one shows data going back to 1901. And in general, if we look at the globe, the northern high latitude land areas have warmed the most out of all the areas globally. So that's kind of the main takeaway. So you can see how Nebraska's historical warming compares to the rest of the U.S. A lot of the warming that we've experienced in Nebraska over the long term is driven by the colder time of year and at nighttime. So the graphic on the left-hand side is showing you the winter, December, January, February average temperatures. And the graphic on the right is showing you minimum temperatures. This happens to be during summer. So, and you can just kind of focus on these blue trend lines here, where we see the strongest rate of warming during the colder time of year and at night, during nighttime temperatures. Okay. One thing that you may have noticed is, in general, the length of the frost-free season, the kind of bounding it by what's the last date we go below freezing in the spring and the first date we go below freezing in the fall. What's that length of the growing season? That has increased overall. So for Nebraska, it's about a week over the long term, and that's increased more for the western U.S. and kind of the northeast U.S. But we have seen an increase in the frost-free season. If we look at precipitation, Nebraska, we've gotten slightly wetter. There's a lot of variability from year to year, but we've gotten slightly wetter overall. And in this graphic, so anything in green has gotten wetter, brown has gotten drier, and anything in the gray here is no significant change over the long term. But in Nebraska, we kind of lie right on this, on the western edge of this kind of pocket of wetter conditions, kind of in the north central U.S. and the northeast as well. But this part of the country has gotten wetter overall. In terms of how we've received our precipitation, is it coming more in heavier events, heavier rainfall events? And that has tended to be the case overall for much of the country. The area that has gotten wetter, kind of this part of the country, has also seen heavier precipitation events. And you can think about those as being more likely less effective precipitation, where you're getting more intense events and greater runoff potentially, and so less is able to infiltrate the ground, and we're able to make use of it. So more of it is running off, likely when you get these heavier precipitation events. In terms of frequency of river flooding in the U.S., this particular graphic goes back to 1965. So anything in these blue diamonds have seen an increase in flood events, and anything in the brown has seen a decrease in flood events. And so this, these images again is showing an increase in flood events kind of for Nebraska and portions of the Dakotas and into Iowa, whereas other areas have seen a decrease. And this is a function not only of precipitation but kind of land use practices, and there's other ways in which we can impact flooding because of land management. And so it's not only a factor of precipitation, but land use as well. Okay, so something that we also tend to look at in Nebraska in terms of water and what's going to be running through the Platte systems in particular is snowpack in the Rocky Mountains. And overall what we've seen is a lessening of snowpack. There's less water in the snowpack and an earlier snow melt. Of course it varies from year to year, but over time there is less snow in the Rocky Mountains, therefore less moving through the system that impacts Nebraska. Okay, so let's get into some projections. So I talked about climate models and kind of these different scenarios that are run, and what I'm going to show is two model scenarios. So when it says curb emissions, that means that we try and mitigate future increases of CO2 and other greenhouse gases. And the business as usual is that we don't. We keep on kind of doing what we're doing. So there's two different scenarios that are given here. But looking at mean annual temperatures, so for Nebraska, in this scenario, in the top here, going out decades into the future, we're looking at about a 5-degree Fahrenheit increase. So for Lincoln, that would mean that our average annual temperatures would look more like Topeka than Lincoln. Topeka currently, as opposed to Lincoln. And you can see much more red, the darker colors here, so about a 9-degree Fahrenheit increase on an annual average temperature basis. So that would mean Lincoln would look more like Oklahoma City does now in terms of average annual temperatures. So looking at precipitation, and this has been fairly consistent in the climate models. Here we're just looking at one scenario, and I'm showing winter, spring, summer, and fall. And the consistency is that during the colder time of year, winter and spring, we're projected to get wetter, whereas during the summer, we're projected to get drier. So on average, 20% drier for Nebraska for summertime. That's typically when late spring and summer, that's when we receive our highest rainfall amounts. So reduce that by 20%. That's what the projections are for summertime. And for winter and spring, conversely, that's for 20% or more precipitation than what we have now. So an impact, particularly in spring, might be, historically we have seen spring get wetter overall, and that trend is projected to continue. So you can think about the ability to get into the fields if we're going to have more rainy days, more moisture during that time of year, and what sort of impacts that would have. And with the warming overall, winter, we would likely see less snow events and more rain events during the winter time in a warmer climate. So summer, you can think about potential impacts if it's projected to be 20% drier, and we're also going to be 5 degrees or more warmer. So you can think of what sort of impacts we would have with the combination of those two changes. How much moisture is in the soil? So that's what this graphic is showing. So middle of the century and end of the century. You can see if we just kind of focus in on Nebraska, given the warmer conditions overall. The previous graphic I showed talked about summer getting quite a bit drier, so kind of a longer growing season, a longer time. The grass, the crops are able to grow and use moisture in the soil. Combined with the warmer conditions, there's going to be a lot more use of that water in the soil. Therefore, the amount is projected to be less than what it is now. So those are kind of averages, projections that I've shown. And we can also think about extreme events, and those are some of the high impact events. For example, number of days we go above 90 or 100 degrees in Nebraska. Kind of how will that change looking at this high end? So you can think about this as our average climate, and this is what it is now. And in a new climate, so I talked about a 5-degree warming, say this shifts by 5 degrees. So then our extreme heat events used to be in this category. So now they're kind of in this category. So everything would be kind of shifted toward this more hot events and less cold events. And that's indeed what the models are indicating is 3 more weeks of days where we go above 95 degrees across Nebraska. So we can think about what sort of impacts in terms of crop stress, water use, energy demands, those kinds of things. Whereas conversely, likely much fewer cold events during the winter time, so less of a heating demand. But possibly if we don't have these cold events to kill off certain pests, then we might have new species potentially coming into the area, or less winter die-off of certain pests and species. So this gets at kind of these occurrence of hottest and coldest days of the year. So on the top we have the coldest days of the year. So if we just focus on this, and this is the curbing emissions scenario, this is the business as usual scenario. So even if we curb emissions now, you know, the temperature change in the coldest days of year, they'll get quite a bit warmer than what they are now, so not nearly as cold days, whereas the hottest days of year, that's what's in this bottom graphic here. So the projected temperature change on the hottest days of the year, they're 95 to 105. That's kind of the temperature of the hottest days of the year here in Nebraska. So an increase by 3 to 4 degrees. So we're shifting those warmest days to even warmer. So as we think about kind of these projected changes, these are some of the things that I consider to be some of the key issues that we need to be thinking about is warmer at night, and particularly during the summer if we're warmer at night, and cattle don't necessarily have the ability to cool off. You know, it's a different climate than what it is now, and if we don't, if our nighttime temperatures are not cooling off, then what sort of impacts will that have to animal health and human health? Warmer during the winter, so less snow, more rain events, less winter die-off of things that we depend on dying off currently, and what sort of new species could potentially be emerging. A longer freeze-free season is what I mentioned, so if we have a lengthening by several weeks of the growing season, what sort of considerations will we need for that in terms of what we grow and how we grow it. And then precipitation changes, wetter during the colder time of year, wetter during winter and spring, drier during the summer. So thinking about terms of water storage, perhaps, if we get more precipitation, where should that be stored? And then water demands during the warmer time of year in terms of agricultural uses, recreational uses, municipal uses, kind of those competing water resources. What will those considerations be? More evaporative demand during the summertime and during the growing season. It's going to be warmer, it's going to be more hot days. How much water will those crops need to be using? That's certainly a consideration. As well as, so I mentioned increased competition for water resources among the different users. And then more extremes. That's kind of a general theme that really holds true for any area, is more extreme events of heat, drought, heavy downpours, kind of how will we be able to cope with overall more extreme events. And so some things to maybe think about. So I've shown historical trends and I've shown future projections, and one kind of message that I often talk about is the magnitude of changes in the future will be greater than what they have been in the past. So in the past we've seen about 1.5 degrees warming, and the future projections are about a 5-degree warming. So that rate of change going forward is going to be different than what it has been in the past. And in terms of adaptation to a new climate, there's not necessarily a one-size-fits-all or something that works best for certain for all sectors, but we can learn things from different sectors. And I tend to think that agriculture in a place like Nebraska, because there is such high variability from year to year and has been in the past, we go cold years to warm years, we go wet years to dry years. We already experience this range of variability that Nebraska is really well positioned to look at adaptation and mitigation measures to future climate change, because it's something that we already experience from year to year.